3, 2, 1. All right, so hey everybody, welcome to the second half of the Minerals Lab. This is our second and final two-part lab, actually. So after this week, all of the labs are contained within a single session. So we are following up on last week, and last class made a bunch of references to this week being focused on igneous rock building minerals, and I apologize for mentioning that repeatedly because I looked more closely at the lab and realized I had been thinking of a similar lab that I had done over at Santa Barbara City College. So some of those minerals do show up in this lab, but not specifically in the context of this is what shows up in igneous rocks. So that's something we'll get to more next week. So in terms of what we are doing this week, this lab first has a couple of exercises that introduce minerals with unique properties. And then you get to apply your knowledge from last week, studying properties such as streak or hardness or cleavage on their own. You get to kind of apply them together and do some introductory mineral identification. So instead of working with one property at a time, you'll be using the properties together as part of a trial and error process. And I'll walk you through how you're going to do that. Basic mineral identification usually ends up involving using a flowchart, and that's sort of a built-in crutch / helping method that is used until you get more practice. Because I will say, from having done a lot of mineral ID, from having taught this in similar classes before, is that mineral identification is kind of like spotting birds or like playing the cello or something like that. It takes practice, and I want to encourage you to come to me often with, Professor, can you tell me if this is one or two planes of cleavage, or can you tell me if this is metallic or non-metallic? Because those are things that take time to spot instinctively, and I can help you go the right direction with them during this class, in case stuff is confusing. And I know that mineral ID can be stressful for some people because of that, and I'm here to help and answer questions to hopefully relieve that stress as much as possible. And I'm also going to walk you through the resources you have available. Don't panic, take the time you need. It's designed so that you can finish it in the class period, but if the time crunch is too much for you, I do not care if you do it outside of this period. I will very happily answer emails, and I can meet outside of class just as long as you give me a heads up. Thursdays and Fridays, I'm usually doing Instacart most of the day, actually, but I actually can usually make time to meet while doing that. I just will do it over my phone, but I'll be out and about doing that. So any questions about that, actually, before I move on to this announcement? Okay, I can make a window for chat. That's great. Awesome. Okay, so Dr. Bird wanted me to mention that there is now walk-in counseling for STEM majors. Walk-in a sense. So again, this is my first term here, so I still don't know that much about how things work, but AVC usually has offices where you can walk in and meet people to talk about what options you might have career-wise if you're majoring in engineering or chemistry or geology, as well as what degree requirements might be and what kinds of resources are available on campus. Obviously, that's not happening in person right now because we're doing this geology lab from my apartment, which does have a lot more minerals than usual than the average person's apartment, but is not designed as a geology lab. But this is going to be done via Google Hangouts, actually. So if you are considering majoring in a STEM field, and especially if you're a geology major, during the times listed here, there are 2 staff members available for counseling. Which one you go to depends on whether you've done classwork outside of AVC and what your major is. So if you're thinking of majoring in geology, I am pretty darn sure it's Crystal Ibrahim you're going to want to contact. And to do these walk-in hours remotely, you log into your AVC Gmail, and when you're in Google, there's the Hangouts feature, the chat feature on the left side. There will be a little plus sign next to your name, and then that is a feature that lets you add contacts. And so you can then search people who are within the system. So Crystal Ibrahim will show up as being within the system, and then you can chat with her during the designated hours when she's available. So I recommend doing this if you're interested in majoring in STEM, or if you are already, especially just as a way to be more connected with people on campus. Also because, again, I find even teaching, there's this weird disconnectivity, and it's nice for me when I do say talk to or meet Dr. Bird, because it's like, okay, I'm not just doing this in this isolation. I'm not just like a random person doing this in a classroom. Speaking of Dr. Bird, also for geology majors, or if you're considering geology, or if it's even interesting to you, there's actually now a geology majors page on Canvas, and it's a bit of a work in progress. It's set up as like a completely separate course from this. There's not very much there right now, but if you're a major or if you're considering being a major, send me an email and I can add you to that. And it's a way to connect with the faculty and other majors, and we're kind of trying to create more opportunities for those interactive moments, given that we don't have face-to-face classes right now. A lot of interactions happen just in the classroom and in the hallways, and that's really limited right now. So any questions about these? Not directly class related, and I apologize for the poor quality of this image. I tried to export, the PDF shows up like this, and Acrobat was being a nightmare and would not let me export it as a JPEG, but I will also put this up on Canvas I'll put the flyer up on Canvas so you can view it there also. Questions or thoughts or anything there? Cool. So now for something a bit more directly relevant to the course, I am building in a chance for extra credit. So I actually really like extra credit because I think it's a way for students who are especially motivated to dig a little bit deeper into the science, especially if we're covering very basic stuff. And you can also use it to help with lab scores if you struggled particularly with one lab. So this is a bit of a work in progress because, again, this is my first time teaching here, and I'm also figuring out what is feasible or doable when teaching remotely. But there's two methods to get extra credit here that I've listed that I have done before with students at other schools. And for each one of these, for each one of these, you write a response that is 400 words or more, which is about a page single spaced. And if you do that, and submit that to me, you get 2 points that you can add to whichever quiz or lab that you would like to. So the way I'm doing it, when you submit extra credit, you can also inform me, hi, I didn't do particularly well on this lab, or I would like to add it to this lab. So both of these methods involve submitting a greater than 400 words response. And you can do this twice per term, so you can get a total of 4 points from doing this. The two ways, for one option, you can write about a mineral or a rock. And it could be, if you're the type of person who has rock samples lying around their house, this might be a good thing to do. Or if you're someone who got into geology, or if you ended up taking geology as your science because you think crystals and rocks are cool, this might be a good option for you. So it can be one that you collect, although you might want to ask me what type of rock it is before you write a report on it, because I might be able to help you if you tell me where you found it, or one from a mineral collection, like one that you buy at a store or a mineral show. And the main thing you need to address is where it was found, and write a little bit about the geologic context. And that's something I can help you with if you tell me what you're thinking of writing about. And mostly though, it's pretty free for you to write about how you got the sample, the story behind that, and what's interesting about it to you. Because again, you are not necessarily going to have a lot of in-depth knowledge about the temperature a rock was formed at, or the optical properties of a mineral, but you can at least start to scratch that and talk about how it's interesting to you. You must also include a picture. I need to have a picture of whatever you're writing about. And then you can also do a hiking report. There's a lot of geologically interesting places in California, and the Antelope Valley is surrounded by features associated with the San Andreas Fault, so there's that to start with. Now, if there's a place that's geologically interesting or even has cool rocks, you can visit there on a hike or a walk, or even just a brief sightseeing stop, and write a report on that as well. Now, if you find an area interesting, like, oh, cool mountains or volcanoes, but you don't really know the specifics, I can help with that. I have some resources on hand. I have a copy of this book, Roadside Geology of Southern California, which is really good for just doing amateur geology along California's roadways, and it does cover the Antelope Valley. So there's a good chance that I can look up and give you some background info. I also have a field guide to the San Andreas Fault that covers the Antelope Valley. And you must include at least one photo with this also. But I will put this up on Canvas also, but does anybody have questions about this? And there may be other methods I think of for extra credit too, but these are the two that I have right now. And in terms of when these would be due, I would just need them before the final. So I recommend not leaving it till the last minute to do a bunch of extra credit to save your grade, but you have some leeway in when you turn these in. I'm just checking the chat to make sure I don't miss anything there. Doesn't look like it. All right, so moving on to, that's about it for the announcements. So then the rest of today's presentation will be relatively short because we covered a lot of the important background info last time. And with mineral identification, a lot of it does come down to practice. There's not a lot. It's hard to get much from there. It's hard to lecture about it in a way that will accurately give you a sense of what you're doing. But I'll basically be walking you through the resources you have, recapping some of the properties that you will now have to think of more together and in context, because today's exercises are going to be about using the properties together to actually determine what type of mineral a particular sample is. So the samples you'll be working with are actually M1, M2, M3 in the picture of the mineral tray from last week's lab. So we're going to be working with the exact same minerals that you did the exercise on last time. So I will say that if you don't understand some of the basics from last week, like what luster is or how the Mohs hardness scale works, I recommend reviewing that before you start this lab. And one thing to remember is that we have all of these properties, and some of them stick out to us more than others. The human eye goes to color pretty fast, and color is useful to a point, but it's not always perfectly diagnostic as to what a mineral is. On the next slide, you'll see the picture of a bunch of samples that are green, red, orange, and brown, but are all calcite. They're just colored differently by different impurities in the mineral. And impurities are just little amounts of magnesium or manganese. Does anybody actually remember what element will cause minerals to be pink? That's something I briefly mentioned last time.
Wasn't it iron?
Good guess. Iron tends to make things more red. What about like a pink color, like this mineral here? This is actually a specific mineral that has the element in question. I mentioned it this lecture earlier also, and it's also a metal. So it's manganese. That's not super important for the lab, but manganese is generally what gives minerals the pink color. And this necklace I happen to have actually is made of rhodonite, which is a pink version of hornblende, basically. Hornblende is a mineral from igneous rocks that we actually talked a bit about last week because it has weird cleavage. It breaks with its sides being at like 60 and 120 degree angles. It doesn't make boxy shapes when it breaks. But manganese, there's a version of that with manganese that's actually pink. So I actually have a necklace made of that. Bananas have potassium, Jorge, actually. That's a very good guess. And actually I kind of see where you're getting at, because potassium is actually another element that can give minerals kind of a pinkish color. So I shouldn't say that pink is always only manganese, and the pink that you get from manganese is slightly different from the pink you get from potassium. But yes, Jorge, very good point on that. So anyhow, color is useful to a point, but you need to know when it's useful, and you also need to not only make mineral identification based on that. Luster is often a good place to start, because whether something is metallic in luster or non-metallic, in this particular lab, will tell you what chart you need to use. So you spent a little bit of time learning about other types of luster last week. This week, you're mostly going to want to consider whether something is metallic, whether it reflects all light back and isn't translucent, doesn't let light through at all, or whether it's not metallic, whether it's kind of earthy and greasy like this. This is a geode. Let's see if I can. I don't know how well it's in focus, but does anyone have an idea of what this mineral might be based on the crystal shape and some other similar samples you've seen? I apologize for it not being as well in focus as it could be. So this is actually a type of quartz. This is actually amethyst. It's quartz that's been colored with minerals or with impurities that give it kind of a purple appearance. But it also isn't, it's shiny, but it's not metallic. It's kind of glassy if you look at it. And so non-metallic doesn't necessarily mean dull. It just means that it doesn't shine like a sheet of metal would. And that's something that I'm very happy to have you ask me about while you're doing this lab, because as you just saw with me using my little webcam, it's much easier to see something intrinsically when you're physically holding the mineral than when you're looking at a picture or even a video. So luster plays a role, And then you can also do some identification based on what color a mineral leaves behind when scraped on a porcelain plate, the streak, its hardness relative to other minerals or to objects like nails and fingernails and glass on the Mohs hardness index, and then cleavage, which is how the mineral breaks. And cleavage is, again, cleavage takes practice to get used to, but it is really important to understand cleavage because cleavage helps us separate a lot of minerals that otherwise look really similar. There's some minerals that are black that are found in igneous rocks that look really similar, except they all have distinct cleavage, and that can help you tell them apart. So does anybody actually, and one of those is biotite, which is shown here. This is actually a sample from one of my rocks from Antarctica, and this is an example of what a lot of rocks, and especially a lot of rocks formed from magma, look like under a microscope. A jumbled mix of minerals, and the minerals end up actually looking different under a microscope than they do in large sample. But this is actually what a type of mica, the black colored mica, biotite, which you'll see in this lab, looks like under a microscope. So before I do a quick recap of these different properties, does anybody have any questions about anything I've described here? Cool. Something else that it's not for this lab necessarily, but this is a feldspar crystal that shows twinning. You can see there's two crystals kind of grown together. And if you take more geology classes, you'll spend more time looking at like how crystals grow. You'll also notice not all the crystals are the same size. Mineral crystals grow to be different sizes, and that kind of ends up affecting what they look like when you're actually holding them or what they look like under a microscope. So color is useful to a point, but not always diagnostic because these are all calcite. And notice you can kind of actually see that the cleavage is the same in all of these. It's a little more smooth in this sample, but you can see that these all have sort of rhombus-like cleavage. Calcite has cleavage at not boxy angles, at not 90-degree angles. So the pieces aren't exactly cubes or rectangles. They kind of look like little rhombuses. And you can see that even though not all of these have the same perfect shape, they're pieces that all have the same basic shape. They all look kind of like rhombuses. This one, and this one, and this one, and this one. These ones are kind of messed up, but you can see it a little bit. And that tells you that cleavage often more accurately defines a mineral than color, because the cleavage is actually affected by its internal crystal structure. Color is often caused by tiny amounts of stuff like manganese or maybe potassium. Potassium actually often is a more important part of the mineral. So we'll actually see that potassium does actually lend a distinct pink color to one type of feldspar that you'll see a lot. But then stuff like little bits of copper, sometimes iron staining, like calcite doesn't really have iron in it normally, but little bits of iron will get in and cause it to be rusty. And you just kind of have to know when color is diagnostic and when it isn't. And that unfortunately over time comes with a degree of memorization. As you spend more time in geology and you see minerals over and over again, you start to recognize, okay, calcite tends to be all different colors, but something like orthoclase feldspar, which is the type of feldspar that has potassium in it, that does usually tend to be pink because the potassium is actually part of the main chemical formula. And I'm not really having you memorize formulas, but sometimes looking at the formula can be really helpful to give you a sense of what's actually in the mineral. And you'll see that the formula for orthoclase feldspar actually does have potassium in it. The formula for calcite does not have potassium, does not have iron, does not have manganese, does not have any of these other elements that cause the colors, but the tiny amounts of the colors do cause a noticeable difference when we see them. Does that make sense? Does anybody have questions about that? So luster then is how a mineral reflects light. And oh, I'm sorry, my thing got messed up. So the luster is how a mineral reflects light. And you don't really need to worry about all these terms. For the most part, for this part of the lab, you will want to consider whether something is metallic or whether it isn't metallic. And notice how many of these types of luster involve some degree of shininess. Adamantine and glass and vitreous are kind of just two slightly different variations of a glassy appearance. And I do find that still images don't do the best job with this, because often the best way to understand luster is to have several different hand samples of a mineral It's not going to be, this again is not the best example, but this is a piece of quartz, and you can actually, it's sometimes really helpful to look at the broken part of a mineral. So this is a crystal I bought where you have a very well-formed crystal face that's really shiny. Quartz doesn't have cleavage; it fractures, but you can kind of see when it's broken off. There's a little bit more parts of it that are see-through. Like there's some parts of it that are like a thin layer, and it doesn't reflect all the light back at you the same way that this is fool's gold. This is a piece of pyrite that I have on me, and this has metallic luster. And you can kind of see how it's twinkling as I'm rolling it around because it reflects all light back at it. My room is not that well lit right now, but this is still twinkling because it's reflecting all the light back. Most minerals actually are not metallic. There's a relatively small number of minerals that are, and they're often usually minerals that you find in hot springs and in mining, or in like veins along with like in mining areas. You find them like pyrite, arsenopyrite, which is like an arsenic version, galena, sulfides. But anyhow, metallic versus non-metallic is what you want to focus on. Then we have streak, which is useful for some minerals, but not for others, because a lot of minerals produce a streak that looks the same. The flowchart for today will actually give you a sense of when streak is a useful qualifier or not. And again, you sadly don't have the ability to pick up mineral samples yourself and grind them into a porcelain plate and see for yourself. There are, however, a number of videos from last week that show certain mineral samples giving a streak or not giving much of a streak, and you will want to continue to refer to those this week. And the reason that some minerals have a different streak than they appear color in hand sample is because a streak is giving you basically one layer thick of the mineral. And minerals will look different in just one layer than they do when you kind of stack the crystals up. Pyrite actually doesn't leave a gold streak. Pyrite leaves kind of a lead colored streak. And that's one way to identify pyrite. Gold does not leave a streak like this. It's also not always useful because some minerals are going to be harder than the porcelain plate, and they will actually physically destroy the porcelain plate when you crush the mineral into it, rather than the mineral getting destroyed. And that's also something to be careful with in the videos. Make sure that you actually know whether it's the mineral that's breaking up or whether the plate itself is being destroyed. Going to really quickly check the chat to make sure I didn't miss anything. But does anybody have questions? We did cover this last week. I'm just recapping. And then hardness is a relative scale. Different minerals are, it's a bit arbitrary, but it was tested out. Different minerals are assigned different numbers on the most hardness scale. So talc, the softest mineral, is assigned number 1. Diamond is assigned 10. Diamond is the hardest natural substance known. In between them, there's a number of other minerals that are set as 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And I'll get to your question in just a sec, Gabrielle. And then common objects that would be easy to take or that you might have on you, like a copper penny, human fingernails, and glass plates or pocket knives or steel nails are all used as reference numbers. So for example, if you're trying to figure out whether something is quartz, one way to do that is to compare the sample that you think is quartz to a steel nail. Quartz has a Mohs hardness of 7. The steel nail has a Mohs hardness of 6.5. So when you scratch them together, which one is going to be broken down? The steel nail or the sample of quartz? Quartz is a 7. Yes, precisely, because quartz is a 7, the steel nail is a 6.5. So if you crush them together, what you'll actually see is the quartz will cause the nail to break apart. And in relation to Gabrielle's question about, so she asked if a mineral is harder than the porcelain, what could streak be checked on? The thing, you say it has no streak. Streak is only in relevance to the porcelain plate. Minerals that are harder than 8 are considered to not form a streak. So diamond does not leave a streak. Corundum does not leave a streak. Topaz does not leave a streak because if you, quartz does not leave a streak. Actually, if a mineral is the exact same hardness as another mineral or as a substance, they will not destroy each other. Things that are the same exact hardness will not crush at all. So that's one reason, again, why actually streak is only useful for some minerals. It is 7. Yes, I misspoke there. Streak is only useful for minerals that have a most hardness softer than 7. Of course, it turns out that many of the minerals that do leave a distinct streak are pretty soft. Pyrite is actually pretty soft. A lot of the other lead and sulfur minerals are also pretty soft. Any questions here? So again, for this, you'll want to look at the videos from last week and pay attention to what is being scratched in the video, the mineral or the object itself. And then there's cleavage and fracture. And I actually have a little video here I'll jump out of to show for a moment. But cleavage and fracture refer to how the mineral breaks. And remember that they have nothing to do with the actual crystal form. So I mentioned that this is quartz, and you can see that there is a nice crystal form. But does this sample have cleavage? Is this cleavage, this nice form you're seeing here? Yes, it's not cleavage. This is how the crystal grew, and you can see that somebody kind of took a hammer to this to lop this off and put it in a mineral show. And when you it's not easy to see in the video because the focus is not that great, but you can see that it doesn't form a flat surface. It forms kind of a rubbly surface with some curvy parts. So not all minerals have cleavage, but some minerals do break along flat planar lines. So calcite is one example of that. You hopefully were able to see when looking at the picture of the calcite samples of all different colors. Hopefully you were able to see more this time how those samples of the same mineral all had really, really similar cleavage. They were broken off pieces, and the pieces were all about the same shape because the mineral, based on its crystal structure, breaks the same way pretty much always. So some minerals break in just one dimension. Micas kind of tend to peel off in sheets, whereas feldspars, oh, and Viviana, I saw you answer that also. Awesome. Feldspars tend to break in 2 dimensions. So when you saw the samples of the feldspars and the pyroxenes from last week, you saw that like the sides and then the top and bottom would have nice smooth surfaces, and cleavage planes tend to be smooth and shiny in general. Whereas the front and back, the 3rd dimension was kind of all rubbly. It hadn't broken in a regular way. Actually, I need to double check what the cleavage of pyrite is. Jorge, I'll double check that. I think it may though. I think pyrite does have cubic cleavage, and so he asked if pyrite has halite cleavage, and halite cleavage is when you have cleavage in 3 dimensions. When a piece breaks off, when the sides, the top and bottom, and then the front and back are all smooth, beautiful cleavage surfaces. And halite is one example of where the pieces break off in blocky shapes. The one plane of cleavage is going to meet the other plane of cleavage at 90 degrees. And don't overthink that. I'm basically indicating that some minerals kind of make blocky or rectangular shapes when they break. Others make more rhombohedral shapes. So pyroxene is one, or excuse me, amphibole is one mineral that has 2 dimensions of cleavage where the mineral the pieces kind of look like this because the planes meet at 60 degree and 120 degree angles. The pieces kind of end up being broken off in these rhombus shapes. And the same is true of calcite. And I am going to briefly step away from the presentation to do something. Let me see if this behaves. Okay, to do something to show a variation of something that I usually like to do in class. Is the YouTube video visible to people?
Yes.
Yes.
Okay, let me know if the sound is messed up. It should be fine this time. But this is someone breaking calcite, which I normally like to do myself because calcite breaks up really nicely and consistently. But watch what happens as he takes a hammer to this sample of calcite. So you'll see it made a pretty clean break, not a lot of debris. What do you notice about the shapes of the pieces compared to one another? Are they all different shapes, or are they all more or less the same shape? Like, do you see the same?
They're all more or less the same.
They're all kind of these three-dimensional rhombuses. And this is what I mean when I say that cleavage is about minerals breaking in a consistent pattern. Calcite will pretty much always basically do this, no matter what color it is. And yes, precisely, Gabrielle, the shape is pretty uniform. And I like to include that because it's sometimes conceptually a little hard to understand what I mean by cleavage, but it's about the rock breaking, excuse me, about the mineral breaking. Rocks are made of many different minerals usually. Other questions before I move on from that?
No.
So then we didn't really talk about last time, some minerals do actually have distinct properties that can be used in positively identifying them. And I will say you want to be careful. You do still want to be careful with these special properties because you do still also want to check the cleavage and the luster and the other properties to confirm something. You generally don't want to assume a mineral is a mineral just based on one property, because sometimes there is more than one mineral that does something. Most minerals that are magnetic are magnetite, but there's a couple of other examples as well. So it's, again, useful to be familiar with the mineral's run-of-the-mill properties, like cleavage and hardness, because the special properties are good for confirming that something is a mineral. It's not always the best place to start. But some of the properties really do jump out. So something that unfortunately you don't get to do because we're not doing this as a hands-on lab is that you can use magnets to attract some minerals. You can see this person is just using a metal magnet to keep this rock suspended, and that's because this rock has magnetite in it. And magnetite is attracted to metal magnets because it contains an oxidation state of iron that is magnetic. Usually iron is not magnetic in rocks, but magnetite contains the oxidation state of iron in which it will be attracted to metal bar magnets. And the cool thing about magnetite is actually it's commonly found in tiny amounts in lava. So when that lava cools, the magnetite will have been pointing in a certain direction based on Earth's magnetic field. When the lava cools, that actually sort of freezes that in time and preserves that. And so scientists can look at lava rocks and look at the orientation of the little flecks of magnetite to learn about Earth's magnetic field, which is really, really cool, I think. And then some minerals react with acid, particularly carbonates. So calcite is the best known carbonate mineral, and they're called carbonates because they have CO3 in them. They have the carbonate polyatomic ion in them, and you don't really need to worry about that. But CO3 looks really similar to CO2 in its chemical formula, and that's because it actually does get easily turned into CO2 gas. So some rocks, if you pour acid on them, actually make carbon dioxide. If you pour acid, particularly hydrochloric acid, on calcite, what'll happen is that the acid will react with the rock and it'll produce carbon dioxide, which is what the bubbles are, and then water. So not all carbonate minerals do this. Dolomite, which looks really similar to calcite, but just has some magnesium in it, only fizzes if you powder the rock. And so the fizzing can be used as a way to tell apart calcite from some other similar carbonates. And then some minerals have a unique texture. Talc, which is what you find in talcum powder, and it's the softest known mineral. It's the one on the most hardness scale. It feels slippery and slimy to the touch, and that's one reason why there's a rock called soapstone that is actually mostly made up of this mineral, talc, and that rock feels slimy to the touch, and that's why they call it soapstone. Some other minerals smell or have a taste, believe it or not. You want to be careful with that. There's one type of, there's a variety of pyrite fool's gold that has arsenic in it that smells like garlic. So touching it is not believed to give people enough arsenic to cause problems, but you definitely don't want to eat it, even though it smells like garlic. It's surprisingly smells good. And then some minerals don't smell good, like sulfur. Like sulfur produces the rotten egg smell. But then some minerals actually taste like rock salt tastes like salt, and you obviously want to be somewhat cautious about putting a sample in your mouth that other people have been handling, especially during COVID. But if you're not cautious, or if you believe it's relatively safe, the salty taste is diagnostic. And there's potassium chloride. Potassium chloride also has a taste. It has a really, really nasty bitter taste. But some minerals have a distinct taste that humans can pick up on. And then there's some with cool optical properties. This is ulexite, which is it's a mineral with boron in it that you actually find out in the desert. It forms where oceans dried up in the past, and its crystal structure gives it some really cool optical properties. You can actually see an image if you put it on something else. It's kind of functions like a fiber optic cable. And a piece of ulexite cut to the right thickness, you can put it over a book and read the words underneath it because it forms such a nice image. So some minerals have really, really cool special properties. And there's another diagram here that has a couple of other ones. Some minerals are radioactive, so you don't really want to go near them. Hence a Geiger counter is helpful to figure that out. Some minerals are fluorescent. Actually, calcite fluoresces in some cases, and then there's also a lot of minerals that occur alongside calcite that produce these pretty colors. This is from the Omea White Knob Quarry, which is not super far from where y'all are. It's in Lucerne, which is in San Bernardino County. I've been there on a field trip, and it's where they've been mining calcite to use in industrial purposes. And you can actually see in the tailings there, the piles, you can see really pretty colors like this because the minerals fluoresce under ultraviolet light. And then actually calcite has a lot of cool properties. Calcite, if you cut it to the right thickness, will make a double image of whatever is underneath it. That's not something you'll worry about too much for this lab, but I just think it's pretty cool that it exists. So any questions about special properties or kind of what kinds of things minerals have? And that's not a completely exhaustive list either. We're not working with any radioactive minerals for this lab because that's really dangerous. I mean, we'd be working with pictures of it, but we don't normally do that. So sorry to get your hopes up there. So today's exercise is putting together a lot of this knowledge for mineral identification. And something I should have emphasized more last week are the resources you have available. You can review the slides and notes from last week, and I also put up the intro lecture from last week on YouTube, so you can either access it on the link to the YouTube playlist that's on the front of Canvas, or I also have it as a file if you just want to download it and watch it. It's worth having a tab that has Lab 3A open because you're going to need the videos from that lab, and you're going to need the picture of the mineral chart from that lab. And the other thing you'll want to look at is, if you didn't already do this last week, I don't heavily use the textbook, but the online textbook that is linked on Canvas, chapter 3 is rather helpful with mineral identification. So it's very worth, I'd like you to review that if you have not looked at that already. That will definitely help you quite a bit with this lab. And one of your main charts, though, will be this. One of your main tools will be this flowchart, which functions as a step-by-step guide to help with introductory mineral identification. So this is a way to guide yourself. It lets you focus on one property at a time and then helps you move on to the next property. Again, eventually you get to the point where you don't need a flowchart. As you do more mineral identification, you will probably find a flowchart less helpful because it is kind of mechanical, but it does give you a good, like, okay, let's focus on this first and not focus on anything else. Okay, we're done with that. We know for sure whether it's metallic or non-metallic. Good, let's figure out the next property to look at. So for example, and this is also in Canvas, but that's why I've brought up luster. The first step in the flowchart here is to figure out whether it has a metallic or non-metallic luster. And there's several different charts that you can use then. Those charts are accessible through a link that is within Lab 3B in the intro text, but I'll also show you what they look like on the next slide. And what this does, it helps you determine one property at a time, and it also helps you do some process of elimination. There's several different charts that use different criteria for determining minerals, and you want to first figure out what chart you're going to want to end up at. So again, check with me if you're uncertain whether something is metallic or non-metallic, or if you come across a case where you're not sure what the cleavage is. Now, I've kind of been saying color is not super helpful for minerals. It is sometimes. For non-metallic luster, whether something is light colored or dark colored actually does play a role. A lot of the rocks with non-metallic luster are formed by lava. They're formed in igneous rocks. And there is a distinct chemical difference between mafic igneous rocks and the mafic minerals in them, aka the dark colored ones, and felsic igneous rocks and the felsic minerals that are in them, aka the light colored ones. Whether something is light colored or dark colored can be a little bit tricky sometimes, because a lot of minerals are just black or white, but then some are pink or gray or kind of greenish. Check with me whether something would be considered dark or light first. Light tends to be white, but also gray and pink. Dark is going to be either black or green. Green is really considered a dark color for mineral identification, because the greenest mineral, the minerals that are dark green are often olivine, and olivine is a mineral that has a lot of iron and magnesium in its chemical formula, and that actually is to a big extent what determines whether a mineral is dark or light. But I'm getting a little bit ahead of myself, but I do check with me about color if you're uncertain whether something qualifies as light or dark. So there's a chance the answer won't make sense to you, and that's fine. Then you can check with me and I can walk you through whether I think you followed the steps correctly or whether there's something you might have gotten confused on. So any questions here before I give you a glimpse at the identification charts? And also, no two flow charts are the same. I've used different flow charts for different places. It's a tool very much. It's not an absolute. This is how geologists always figure out what minerals are. It's a starting tool. And if it seems frustrating or mechanical, it's something that mineral identification is something that becomes less frustrating and mechanical with practice. Definitely. So these are the 3 charts I'm talking about, and they are accessible on Canvas. So the end result is the minerals in the rightmost column. The minerals in your tray are all minerals that are shown in this rightmost column. So you won't be using all of these, by the way. It's not a process of you need to find all of these. There's I think 14 mineral samples, and there's a lot more minerals here. But I definitely, one thing I recommend doing is for the mineral samples in your tray, it's worth having a notebook or a Word document open where you maybe make an entry for each, like M1, M2, and you write down the properties as you figure them out, like M1, non-metallic and no cleavage. That, I don't know if that's what it is, but I'm just using that as an example. And good note-taking can really reduce potential for confusion here. So I recommend writing down. I definitely recommend writing down the properties that you determine to keep organized, especially if you end up jumping from one mineral to another. Like if you figure out that something is metallic, but then you get stumped and decide to move on to another mineral, you will have at least written that point down for the starting mineral, and you'll have that information when you go back to it, and you'll also be able to more effectively communicate that to me. So I do find that good note taking helps a lot with staying on top of the information in these labs. And so again, yes, there are 14 minerals. You'll be working with the same set of minerals, so you should be at least somewhat familiar with the samples. This lab is due on Monday, March 1st at 11:59 p.m., and there is not another quiz due that day. So this is the only thing that's technically due next week. And this is the last 2-part assignment that we're going to have. We will have one lab on igneous rocks the week after this, and then we'll have a separate lab on volcanoes after that. And igneous rocks builds heavily on minerals because a bunch of the minerals that you'll see in this lab are important forming minerals for igneous rocks. And if you have trouble with minerals, it makes accurately understanding the types of rock a little harder later on. So this is the time to inform me if you need more help or need me to explain something over again before we start moving into building on this with igneous rocks. That's about all I have for the presentation. Does anybody have questions before I shut the recording off?
No.
Okay, cool, thank you. I appreciate that. I can't see everyone's face when I'm doing this, so thank you. Okay, so that is all for the recording and the presentation then. So